Hello everyone, JCE Connect. I welcome you all for this particular lecture. So in previous lecture we have seen a single angle connected to the gusset plate and designed the section. So here in this particular lecture I'll be taking a double angle connected to the gusset plate on either side. This is a double angle connected to the gusset plate on either side. So we'll design this section. Okay. So here the problem is given as design a double angle tension member connected on each side of a 10 gusset plate to carry an axial factor load of 400 kilonewton. Use M20 bolts of property class 4.6. Assume shop connection. So this is a problem given here. So for the given load we need to assign the section, and after assigning the section, whether that section is safe or not we need to check. That is a design problem. So what is step number one? The step number one here, the step number one, first we have to assign the preliminary section, calculate preliminary section. So to calculate a preliminary section we have a formula, that is TD is equal to AZ Fi by gamma MO, where in this case TDZ is given, that is factor load is given, that is 400 kilonewton is given, factor load is given. Then substitute that here, then we get Az equal to TD into gamma MO divided by F1. Substitute the given load here, then that is 400 into 1.1 divided by 250. You will get 1760 millimeters square. Then whatever area you get here, you increase this area by 20%. Increase this area by 20%. After increasing area by 20%, you will get the area of, that is 1760 into 20% increase, you will get 2112 millimeters square. Okay. After increasing the area you will get 2112 millimeters square. Then you have to search in a steel table. From steel table you have to search in a steel table which section gives this much of area. That to double angle, you have to search double angle in a steel table. Refer steel table and double angle, equal angle. So in this I am referring steel table here. So here I taken page number 18, where properties of two equal angle section provided back to back. Here they mention properties of two equal angles back to back. So here you have to search which section gives you the area obtained. Whatever the area you obtained, which section gives that much of area, you have to choose that section. So here I'll searching. So in my case the area is 2112. You search that one, so you will getting 70 by 70 by here, this one 70 by this, just check this one, you'll get 70 by 70 by 10 mm, 70 by 70 by 8 mm. So 8 mm giving you here this one 70 by 70 by 8 mm. This much area gives you 21.16, 21.16, 70 by 70 by 8 mm. On the steel table, so double angle section you have to refer, then provide, that is adapt to ISA 70 by 70 by 8. So when you select a section from the steel table, so just note it down the area of this section from the steel table, that is area provided. Then it becomes area provided. This section you are providing, so you whatever the area you get, that should be provided area. So you will get that one, 2116 millimeter square. Okay. Then after this, so once you get a area, then the analysis part. Just I'll draw here once again. This is a gusset plate. Gusset plate. The angles are provided on either side like this. Then draw the section. Sorry, this is a section. Draw longitudinal section. Still we don't know how many bolts needs to provided. So next we need to calculate number of bolts. Okay, this is a double angle. Okay, so angle provided here is, this angle is, that is 2 ISA 70 by 70 by 8 we have provided. So this leg size is 70, and again this leg also 70. Okay, then you've also noted down the properties of this one, that is CXX and EXX. So properties of that section is CXX and EXX, that is CXX and EXX of that section. So here I am getting CXX 70 by 70 by 8. CXX I'll be getting 20.2 CXX. We'll be getting 20.2 as a CXX. Then 70 minus remaining, we'll get EXX. That is 70 minus 20.2, 49.8. Okay, this is EXX. So from here I'll mark CXX. This will be CXX and this will be EXX. Okay, so this represents the centroid of the bolt hole provided. Still we don't know how many number of bolts needs to be provided. Okay, this one. So this is the load given here, 400 kilonewton. Factor load is given. Okay. After this, first we need to calculate number of bolts required. So that is again what are the data is given? The data is given here as property class is given 4.6. So FUB will be 400 Newton per millimeter square. Then FU for plate will be 410 Newton per millimeter square. And bolt diameter of bolt is given, that is 20 mm. Then diameter of hole becomes 2 mm more, that is 20 plus 2, 22 mm. Okay, Then after this, calculate bolt value here. Calculation of bolt value. So we need to calculate bolt value. So once we get a bolt value, then the number of bolts can be easily calculated. So this section, this is providing back to back, this will be double shear. Okay, so this plane gives you the double shear, so we need to calculate strength in double shear here. So this is the double shear. So strength in double shear, strength of shear in double shear, so that is VDSB. We know this formula, Fu divided by root 3 gamma MB into bracket NN ANB plus NS ASB. Okay, so taking NS equal to 2, since it's a double shear, so NN equal to 0 here. Then substitute, then calculate ASB. ASB will be pi by 4 20 square, pi by 4 20 square. Calculate this one. Then after calculating, substitute all the values, you will be getting 116.08 kilonewton. This is the strength in double shear. So similarly calculate strength in bearing, that is VDPB. So VDPB formula we are having, that is 2.5 kb dtfu divided by gamma mb. So this is the formula we are having. So again here you have to assume minimum edge distance to be taken 1.7 times of diameter of hole, and pitch to be taken 2.5 times of d. So when you substitute, and you will be getting approximately 40 mm, and also pitch you will be getting approximately 50 mm. Okay, then you calculate kb value. You know how to calculate the kb value. kb is the least of these three. E divided by 3 du, second p by 3 du, third fub by fup minus here 0.25. Then fourth one, when you substitute the value of edge distance and pitch here, you will be getting first one as 0.909, then 0.507, then this one is 0.975. which is the least in this, you have to take it as a kb, that is 0.507 as a kb value, 0.507 kb value. Then here substitute that value here, then it becomes 2.5 into 0.507 into diameter of bolt is 20 into thickness of angle is 10 into 410 divided by 1.25. So for that you will be getting answer 64.98. Then the bolt value will be least of above 2. Bolt value will be the least of above 2. Then the bolt value becomes 64.98 kilonewton. So after calculating bolt value, then you know the load, that is number of bolts to be calculated. The load is 400, then the bolt value is 64.98. So you'll be getting a number of bolts, approximately 6 numbers you'll get. Then arrange those bolts. So already we have been drawn here this figure just to mark the number of bolts. Draw number of bolts. 6 number of bolts we have obtained. 1, 2, 3, 4, 5, 6 number of bolts. And also we have been calculated the edge distance and pitch distance. Mark that one. So edge distance was 40, 50, 50, 50, this also 50, 50 and 40. Okay, so this we have calculated. So mark here. Then after this one you need to check whether this angle, provided angle section, is safe or not. So we have to check, that is next is check. So the first check is, as we know, the tension member fails in 3 modes. So that is strength in gross section yielding, strength in net section rupture, and strength in block shear. That is, we need to check TDZ, then TDN, then TDB3. So let us take first the strength due to gross section yielding. Strength due to gross section yielding. So again we have a formula, TD is equal to AZ into Fy by gamma mu. So here already AZ we have provided, that is a provided area to be taken here. The provided area here is, that is 2116 into 250 divided by 1.1. So you'll be getting answer 480.90 kilonewton. So which is more than 400 kilonewton, then you can say it is safe. It is safe. The next is strength due to net section rupture, that is TDN. Again we know the formula TDN. TDN will be, that is 0.9 ANC FU divided by gamma ml plus beta AZO Fy divided by gamma mu. This is for one angle. Since we are designed for double angle, you have to multiply it by 2. Whatever answer you get, you have to multiply it by 2. Where ANC is connected leg area. So here this one, connected leg area, you have to take connected leg area, and this is outstanding leg and this is the connected leg. So connected leg area will be ANC, we are connected to 70 mm leg, 70 minus thickness 10 by 2 minus 1 diameter of hole into thickness. So we get that as a, sorry, thickness as 8 mm. Thickness 8. Thickness 8. Then we get 352 millimeter square. Similarly, outstanding leg area, that is 70 minus, this is also 8, 70 minus 8 by 2 into 8, we get 528 millimeter square. Then calculate the beta value. Beta value, the beta formula we are having 1.40 minus 0.076, then W by T, Fu by Fy, then Bs by Lc. It should be less than or equal to 0.9 times of Fy gamma m, Fu gamma m divided by Fy gamma ml, and also it should be more than or equal to 0.7. Then you know how to calculate these all. So I have explained in previous problem. So these all, W is the outstanding leg width, T is the thickness of plate, Fi is the yield stress 250, ultimate stress Fu 410 divided by 250, Bs is the shear leg width, that is Bs here to be taken W plus Wi minus T, where W is the outstanding leg width here, outstanding leg width, and this will be the Wi. So here like this, if this is the angle connected to the gusset, this is the bolt, this will be W, from here to here is Wi, this is Wi, okay. Then W is 70 plus Wi is 20.2 minus thickness, we will get Bs as 82.2. Similarly calculate Lc. Lc will be the this one. Lc from the first bolt hole center to the last bolt hole center, that is 50 plus 50 plus 50 plus 50 plus 50. First bolt hole to the last bolt hole center, measuring along the direction of load, this one. So Lc will be 5 into 50, you get 250 mm. When you substitute all values, you will be getting beta as 1.26. Okay, just to compare this value, beta value, with this one, calculate this one and this one. Okay, it should be less than this one and it should be greater than 0.7. Okay, this is beta. Then after this, calculate TDN. Then substitute all values, you will be getting TDN as 510.22 kilonewton. Substitute the values calculated previously in TDN formula, you will be getting 510.22 kilonewton. So the next, which should be more than 400 kilonewton, this is the load given, then it is safe. Next is block shear strength. That is TDB. We are doing checks. There is check due to block shear strength. So we have a TDB1 and TDB2 formulas. So TDB1 formula is what? That is AVZ Fy divided by root 3 gamma mu, one term, plus 0.9 ATN Fu divided by gamma ml. So again you have to multiply it by 2, because for double angle, if it is single angle then no need to multiply, for double angle you need to multiply it by 2. Then TDB2 will be TDB2 0.9 AVN Fu divided by root 3 gamma ml, one term, plus Az Fy divided by gamma mu, then again you have to multiply it by 2. Then AVZ will be what? AVZ will be the shear area. So AVZ will get shear area here. So in this one you have to mark that one. We'll mark here from here to here. This is shear area from here. How much is LV? LV will be 40 plus 5 into 250. So you'll get 290 mm. Then how much is LT? LT is this distance. LT will be this one. This is under tension. This is LT. Okay, so LT will be how much? That is LT will be nothing but EXX, that is 49.8. 49.8. So along the direction of force or parallel to the load, whatever the area, that is shear area, then perpendicular to that will be tension area. This is under tension. This area to be considered as a tensile tension area. Okay, then how it generally fails, it will be like this. It will be like this. Okay, so now this is tensile area, this will be LT, and from here to here it is LV. I hope you understood this one. Then LV will be, that is AVG will be LV into T gross, that is 290 into 8. So you get that one 2320 millimeter square. Then AVN will be, just deduct the number of holes here. How many holes? This is 1 2 3 4 5 and half. This is only half cut. Okay, that is 290 minus 5.5 into 22 into 8. So you will get for that 1352 millimeter square. Similarly, calculate ATZ. ATZ tension area, LT into thickness, that is 49.8 into 8. You will get for that 398.4 millimeter square. Then ATN will be how much? So this is up to the center, then half of the bolt hole has cut. Okay, the net you have to take, that is 49.8 minus half of 22 into 8. You will get 310.4 millimeter square. 310.4 millimeter square. Substitute these all values, AVG, AVN, ATZ, ATN, or TD in TDB1 and TDB2. You will get TDB1 as TDB1 you will get 792.1, and TDB2 you will get 630.7 kilonewton. So both values are more than 400 kilonewton, hence safe. So this is the design problem. So when you assign the section, this one like this, when you assign the section, after assigning the section you need to check this section whether it is safe or not, because the tension member generally will fail in 3 modes, that is gross section eroding, net section rupture, and block shear failure. So if it is passing in all the 3 modes, then the section assigned is safe. So it is very simple. The first step needs to be calculated, that is the preliminary section to be assigned, that is calculate preliminary section. Then after assigning that section, just calculate the number of bolts required Number of bolts required, how do we calculate the first the bolt value, then the load given, that is load divided by bolt value, you will get the number of bolts, then arrange the bolts, then get some properties from the steel table for that particular section, then go on checking, that is three modes of failure, that is TDZ, TDN and TDB. If it is passing in all the modes, then it is safe. Thank you.